In this question, I think the intention is for us to use radians when dealing with the sector area. A equals a half r squared theta when working in radians. But you could instead work with degrees throughout. It doesn't say you have to work in radians, and you would, get the same answer. So if you find radians difficult, or it just feels a bit more natural to use degrees, then go for it. I'm going to stick with radians because that is the intention, but I will talk about how you could do it in degrees at the end. I mean, it's very, very similar. So we've got a semicircle and the diameter is 10, which means this length here is 5 and this is also 5. Good start. But then we're told that AB is the arc of a circle with center A and radius 5. So I could continue this circle round and it would look a little bit like this. So what that means is A to B is also 5, because that's the radius of that circle, and we've got A to O as 5. Now O to B is also 5, because that was the radius of our semicircle. So what we've created is an equilateral triangle, and that is essential in this problem. Then we've got a region R, and it's bounded by that arc, and then the rest of the semicircle, and we're being asked to find the exact value of R. So there's a couple ways we can do this. Actually, the way that I did it was to find the area of the semicircle and then subtract this sector and then subtract that little bit. But a slightly quicker way is to instead find the area of this sector and then just subtract this little bit. But in any case, we're going to need to find this little green area. So I'm going to focus on that. Now I'm going to work in radians. So actually 60 degrees is pi over 3. So all of these are pi over 3. And let's start by finding the area of that triangle. It's going to be a half AB sine C. So a half times 5 squared times sine pi over 3. That ends up being a half times 25 times root 3 over 2. So we get 25 root 3 over 4 for our triangle area. I can then find out the sector area. We've got pi over 3 here. So if I use this formula up here, then for the area, I'm going to get a half times 5 squared times pi over 3, which is going to become 25 pi over 6, which means I can now find this little part here, because it's just going to be the sector, area of the sector, 25 pi over 6, minus the equilateral triangle, 25 root 3 over 4. To get to there then, brilliant. So now to find the shaded area. Well, I'm going to go through this in a couple of ways. The quickest way is going to be to find the area of this sector and then minus the green area. And this angle will be 2 pi over 3 because the two angles will add up to pi radians on a straight line. So AR is going to be a half. Remember, it's a half r squared theta, so a half times 5 squared times 2 pi over 3. Then I'll be minusing that green area, 25 pi over 6 minus 25 root 3 over 4. And this here becomes, well, it becomes 25 over 3, which is 50 over 6. So 50 pi over 6 minus 25 pi over 6 plus 25 root 3 over 4, which is then 25 pi over 6 plus 25 root 3 over 4. Okay, let's just make sure we write it in the form that's being asked for, because it was a root 3. So I'm going to write it as 25 over 4 root 3 plus b pi becomes 25 over 6 pi. I don't think it'll be marked down if you left it like this, but we should try and follow the instruction and write it like this. So method 2 is this is how I did it, but it's not as good. It's going to be more complicated. So we could take the whole semicircle now, and then we could subtract a sector, and then we could subtract the green area, which is equivalent to this. Or imagine subtract this sector and then minus the green area. So method 2, AR is going to be, like, it's just a semicircle here, so I don't really need to use a half r squared theta. It's just going to be pi r squared over 2, pi times 5 squared over 2. Then I'm minusing the sector, 25 pi over 6. So that would leave me with this and just that green bit. So now I need to minus the green bit. So I'm minusing 25 pi over 6 minus 25 root 3 over 4. If I put it over 6, this up here becomes 75 pi over 6. Then I would minus 25 pi over 6 and another one, so I would be minusing 50 pi over 6. And then actually adding on 25 root 3 over 4. Again, we would get 25 pi over 6 plus 25 root 3 over 4, which we could then write in the form required. So a little bit more complicated, but not by much. So the only final thing to say is if you work in degrees throughout, you would just replace, obviously, these by 60, and you would do a half times 5 squared times sine 60, putting your calculator into degrees, you get the same answer here. When you're dealing with the sector, you'd use 60 here, and then it would be 60 over 360 for the fraction, or 1/6. 1/6 of pi times pi r squared. You'd get the same thing, because the half times the third give you the 1/6. And then from that point on, everything's identical. So by all means, use degrees here. The question does not say you have to use radians. But make sure, I mean, it's still good to practice using radians because other questions will make you use it and so on. So that's why my main solution went for it that way. Well done.